Hey everyone. So today I'm going to talk a little about, in more detail, about the different approaches that we tried, what worked, what didn't, and some interesting observations on the dataset. Um, so first of all, I should probably start with quickly redefining the problem because I'm not sure that everyone is familiar with it. Uh, Basically, this image here that is put on the official case it's actually not the same problem. This is object detection, and what we are having here is we are trying to classify an image. Basically, you have the assumption that there is one fruit or vegetable on the image, and you want to predict what kind of thing it is. Is it an apple? Is it a potato? And so on. For example, this is a different problem from the detection, where you're searching for a bounding box of an object, and segmentation is another problem altogether. So just want to know that this image is actually not doesn't represent what the problem is. So basically, the problem is when you have let's open just sample images so that you have an idea of what I'm talking about. Basically, you have this image and you have to predict that it's a banana. There are all sorts of difficulties, like the light is different, and so on. So the first thing that we need to do is to have a look at the data. Can you hear me actually? Because I think the stream broke, or great. So basically, let me just show you the count for each class. Basically, the data is highly imbalanced. There are some classes that have just 22 examples. Of course, it's almost impossible to train a model based just on that. So this was actually one of the reasons that most of our initial ideas revolved about around transfer learning, which is basically you take an already trained neural network that you reuse the fact that there is some intelligence stored in that network already. Also, another difficulty with the data, apart from being, imbalanced, is actually there are a lot of similarities between some classes. I would like to just I would like to show you a quick, this is our confusion matrix for our final model. Just I want to show an interesting thing. So basically, we didn't get any example of this class. I don't know how it's pronounced. Sorry, I don't speak German, but we basically didn't get any of those right, and we always, actually not almost always, but always mistaken it for bananen. And it's obviously those are different types of bananas, and I'm going to show you an example image for both for each class so that you have an idea of what I'm talking about. So this is a normal banana. This is one of the classes, and the other is actually, sorry. And the other is actually a banana that is used for cooking, as far as I understand. I'm not sure if there is a German speaker, but that's what I got with Google Translate. And I would think that it's pretty rich. I mean, it's not surprising that we didn't get any of those right. I mean, as a human, it would be pretty difficult to differentiate between the two. So the main difficulties are the data is imbalanced and some classes overlap, like semantically, not. I mean, yeah, that's the best way to put it. Some there are intersections between some classes. All right, so just all right. So this was our first look at the data, and after we did that, we started, talking about different ideas, what we would try, what could work, what couldn't work, and so on. So one of our very first ideas was the so-called histogram of oriented gradients. It was before the era, it was the main method used for pedestrian classification mainly, actually before the whole deep learning era. And it basically works by taking an image and dividing it into boxes and computing the dominating gradient in every direction. The idea is that the gradient shows the direction of change of a function. So if you take this vector, like the dominating position of the gradient for every box, it captures the shape of the item. But obviously here it's not really a good fit for the problem, because it doesn't first, there are different orientations of the fruit or the item that we try to classify, and histogram of oriented gradients is not going to be able to learn this through training because it's hard-coded. So yeah, it was more of like just a cool visualization, but we didn't really invest anything into using this as a feature extractor. So basically in computer vision, specifically for classification, the main problem is the feature extraction. The classifiers are usually just using some multi-layer perceptron or something standard, but the difficult thing is to actually extract good features. And yeah, our final model, which was convolutional neural network, was actually, it was using similar filters, but they were learned through many epochs. So after this, so this is a visualization of the counts of images per product. And yeah, after that, we had some discussions and decided on what are the approaches that we should try. One of our first ideas was actually the Capsule Net, because it's very fresh, it's still warm. Hinton published that paper in November 2000, and it's a great. It probably has great potential. The results on MNIST are very impressive. It is able to also reconstruct what it thinks a class looks like. So it's more debuggable than traditional convolutional neural networks. We often talk about in deep learning how it's different to interpret, how it's different to do reasoning basically with deep learning models. And Capsule Net is actually better at that, but after training it at, basically we were training it on a single machine, and one epoch was about 4 hours, and after 3 epochs, which was the first night of the dead zone, it wasn't really going anywhere. So we basically also we asked different people what they think about this, and most of the opinions that we heard was that Capsule Net actually requires a lot more epochs to start getting reasonable results. So yeah, at this point we decided that Capsule Net is probably not going to be our final model. And then was parallel to that, we were trying transfer learning. As I said, transfer learning is the idea of taking an already trained neural network and reusing the intelligence that is stored in it, which was obtained after many epochs, many months of training, and so on. we can divide the two transfer learning approaches that we tried in two categories. One is to not train the feature extracting part. Basically, usually convolutional neural networks for computer vision classification consist of two parts: the feature extractor, which are the actual convolutions, and the multi-layer perceptron classifiers, which which, as we said, is they're not that important. The difficult part is the feature extraction in our problem. So basically, with transfer learning, we have two approaches based on transfer learning. The first is feature extraction. The idea here is to take an existing neural network, for example, VGG16, and take the output of its different layers and treat all of them as features. The idea is that when you do this, you will find features that are both local and global in some sense, because you have taken different layers from the network. It's kind of heavy to be used in production because you will need to use the original network for this, and VGG16 is actually kind of heavy in terms of memory mainly. And so this was one of our first approaches, and what we did was get a small sample, for example, 200 images or something, and try with different image sizes, because the image pre-processing here is also very important, and see which layers of the VGG16 give us the most information. This is not our final model, because parallel to that, we found that actually a model trained from scratch gives better results, but it did provide us with an insight of the optimal image size. So yeah, you can have a look at the network. It's basically, if you're wondering what those NPIs are, we are just caching the output so that we don't recompute them every time and save some time. All right, and this is one of our ideas for transfer learning, and the other is to use a pre-trained network and train its convolutions also. So we are training also the feature extractions. We tried that with DenseNet, but it also showed some promise. After training for 15 epochs, as we've written here, it had a reasonable accuracy at 3%. That's top one, not top three. I don't remember the top three actually, but as I said, we already found our sort of final model, which was, the idea is basically, we have so little data. Okay, let me start again. We tried transfer learning because we thought that we don't have enough data, and we thought that training from scratch would actually take a lot of time, but it didn't actually. When we tried it, it started to very quickly converge. It's actually a fairly standard convolutional neural network. It's a series of convolutional layers and max pooling layers, and also the batch normalization is a way to prevent overfitting. We tried different approaches for avoiding overfitting, like dropout and so on. And as you can see, in the classifier part, there is dropout, but in the feature extractor part, it turned out that batch normalization does the best job. This was found empirically. We couldn't it's not like we have a good reason of why that is. I would like to mention here that here this layer flatten is actually where the feature extraction is finished, and from here we have the classifier. And something that I would like to note here is that since these layers that follow after the feature extraction part are fully connected, basically adding a layer here grows a lot the number of parameters. And actually our model, our final model, I think has just one layer less in the classification part from VGG16. And this is, yeah, this is why we think it's more lightweight from VGG16. And yeah, it achieved 90% top one accuracy on the test set, which is completely unseen, and 99% top three accuracy. Yeah, I already mentioned one of the interesting classes, like with the intersection. And yeah, I was actually, expecting more questions or something. I don't know. Are we taking questions from the audience or from the chat? Or
For the people that are watching now is the moment to ask your questions. In the meanwhile, we're going to check out the other channels if someone wrote there. But I think that your presentation was quite good and very descriptive. So let's see if someone is still having something to ask.
Okay.
Just a moment.
Let's just have a look at the confusion matrix while we're waiting. Yeah. Those bananas. I mean, there are also different types of, what was it called? Gelp. I don't know what that is. I don't know that if that's even the right way to pronounce it. Oh, that's yellow. Okay. It's yellow actually. So, so it's yellow something. Oh, I should probably show images of the least represented class, which was the images.
Well, so far we don't have questions in the channels. I think that's because that you were very descriptive. You want to share something else with us?
I don't know. That's really what we tried. I mean, we tried a lot of different approaches, as you heard. It was fun. So,
And you learned a lot.
of course, basically the takeaway is the data is like 90% of the case,
Yeah.
because even in our final model, which was pretty good and has 90% accuracy and so on, it has classes that are completely misclassified every single time. So but we explained the intersection. So
Yeah. So I want to thank you again for your presentation. It was very, very good. And to the people that missed to ask their questions, you're free to write them in the data chat or under the article which Team Cherry made. And
cool.
I hope to see you in the next meeting.
Thanks. It was fun, and see you guys next time.
See ya. Bye bye.
Bye.